Okay. Well, it's time to get started. But before we start, are there any announcements? I think from PhD representatives.
Oh, yeah, don't forget this afternoon the PhD town hall meeting.
Where?
That's for PhDs.
Here. Okay.
At 3 p.m.
Very good. And there's the borrow after here. Yes. Okay. Then, well, let's get started with today's talk. Today we have Sonia, who will take us to the moon, the far side of the moon, and will tell us about the Dark Ages explorer. And we're very much looking forward. Please take it away.
Thank you. Hello everyone, I'm Sonia Kosh, and if you don't know me, I'm also a PhD student. I'm a project student currently working with Leon and with collaborators at Aston and Radboud University. So today in my talk, I will basically introduce you to the Dark Ages Explorer, walk you through its concept, and also touch upon a bit about my own work. So, the bigger picture. The final frontier of cosmology. So when we say it, it's not really dramatic, but it's here and actually talking about the Dark Ages, which is actually the last unexplored era of universe's history. And it's the period when after the Big Bang, we had basically no radiation sources, but the universe was basically filled with neutral hydrogen. But this era actually holds the key to most of the profound questions to fundamental physics, such as the dark matter, the dark energy, and etc. And that's why we are so interested in this era. But for the current capabilities of, for example, JWST, we can only scratch the surface of cosmic dawn and not really probe anything from this era, the Dark Ages. And that's where the 21 centimeter line from neutral hydrogen actually comes as a savior. But there's always a but. So the 21 centimeter line from this era is actually extremely faint. And usually the foregrounds, which is basically the synchrotron emission from our own galaxy and extragalactic sources, those are 7 to 8 orders brighter than this signal. So now you can well imagine the dynamic range that we have to deal with if we want to probe this era. But if we rise above this technical issue, we have immense rewards for us. So where do we draw our inspiration from actually? So if you look at the CMB experiment, so it started off in 1964 when Penzias and Wilson basically discovered the CMB monopole, and then we have to wait almost 28 years for the detection of the spatial fluctuation in 1992. And then we had to wait until 2013 to get a high resolution CMB map. So it's almost like 5 decades of perseverance, you see. That's where we draw our inspiration from. And so, being optimistic enough, I expect to get our first Nobel Prize, I don't know, maybe in 2035 when we first detect our sky average signal, 21 centimeter signal, and then another wait for 30 years and maybe detect the spatial fluctuation as well. So, now here we are going to talk about moon and why do we even want to go to the moon. The first thing being, we have always wanted to. So, since the Apollo missions, actually, if you try to find some articles, you will see these rough sketches of, fictional ideas of placing radio telescope on the moon and having these terms like we will have moon base, we will have lunar radio observatory. So it was there since 1960s. So that's one reason. And the second reason being the others are going. So let's just follow. So there are many initiatives by different countries like US, India, China, Japan, and many other countries who are talking about going back to the moon for different missions and also even targeting the same science cases. So why not we go to the moon as well? Now, this is an example of the dawn of radio astronomy from the moon, as we say, because this was the last year there was a mission called ROSIS, which is like a first radio experiment that was deployed on the near side of the moon, and it basically marked the dawn of radio astronomy from space, or so to say, moon. Now let's come to the real reasons, like why we want to go to the moon. So on the Earth, we have this ionosphere that basically distorts the low frequency radio waves through refraction or reflection and so on. And if we go below 30 megahertz, it basically becomes opaque to such low frequency radio waves. So, and we have this ionospheric cutoff. So if we want to observe anything below 30 megahertz, we need to go to space or to the moon. The next thing being the radio frequency interference, that has been a problem for radio astronomers for quite a while now. But with the recent mega constellation of Starlink, we can clearly see the evidence of the recent. This is a list of the recent papers just based on the impact of the Starlink satellites here. So you can see that the RFI scenario is not going to be good in the coming years if we do not take preventive measures. Yeah, so here comes moon as savior. Why? Because moon, in particular the far side of the moon, offers us a radio quiet environment. We still do not have Elon Musk there, so it's still radio quiet. We have very little ionosphere, and also it provides us with very stable environment because we have no atmosphere or we have no weather that's turbulent that we face here on the Earth. And there has been simulations where we try to show that at like how much the terrestrial RFI coming from the Earth can be attenuated on the far side of the moon. So yeah, things are there. So I think I have motivated you. Why should we go to the moon? And so let's build a telescope on the moon. Now, just few years back, a team of almost 70 scientists and engineers basically came together and did this serious study of putting a radio array on the far side of the moon, right? And from there came a concept called the Dark Ages Explorer, which specifically focuses on the 21 centimeter signal from dark ages. And if you want to know more about the technical details of the Dark Ages Explorer, then you can look up to this paper on the archive. So in its first iteration, the way we envision DEX to be seen as a minimum configuration, which is scalable, of course, having 32 by 32 co-located dual polarized antenna. We want the array to be compact and on a regular grid. We want it to be on the far side of the moon and preferably somewhere in the mid latitude because of the UV coverage and things like that. In terms of frequency range, we are currently focusing on 7 to 50 megahertz, but again, subject to change as the project matures. And now we have assumed an antenna element of 3-meter length. Interesting. The important part here is DEX is envisioned to be working as a 2D correlator instead of the traditional interferometer that we do, the cross correlation of the visibilities or the voltages from two different antennas. So instead of doing that, we want to do a direct imaging via two-dimensional spatial Fourier transform. And why we want to do that? It's because we want to reduce the data rates because with the traditional interferometry, the data rate scales with the number of antennas. And because here we are talking about almost 1,000 elements, so we want to reduce the data rates and also reduce the power usage because anything you take up to space or moon, it's costly. Okay, this is very sad. So I have this little animation of pre-DEX, which is like a precursor instrument to DEX. It's a very small array, 2 by 2 elements, which we are right now studying in order for technological demonstration. And there was a deployment animation for this array, and unfortunately it doesn't work. That's sad. I'm sorry. Okay. And it stops. So where does my work fits into all of this? So what you see here, there has been a very nice study by Zoe where she analyzed 8 different sites on the far side of the moon, which are feasible to deploy radio array. And you see on the top row, 4 of those 8 sites. These are the elevation maps of those sites. And in the bottom row, you see the roughness maps of the corresponding sites. Now, the takeaway message here is just looking at the roughness maps. The bluer, the flatter. So we want a flat surface on the moon to deploy the array to so that it works at its maximum efficiency. And you can see that it's very difficult to find a bluer region on the surface of the moon. Another thing to note here is that when you are analyzing such roughness map, it's a very important, the resolution of your topography data becomes very important. It should match the scale of the features that you want to probe as well. So, Mare Jenny is one of the sites that that was mentioned in the paper is a potential site for such an array. So I have chosen it as my test case here. And also I was fortunate to get high resolution data, almost 2 meters per pixel. And also it checks all the boxes of location requirement in terms of placing such an array. Now for my work, I just choose an 800 meters square region from this data, and then I subdivide it into four 300 meters square region to do a first order surface topography analysis. Now, surface topography analysis is not a new science. It is done every day in order to do terrain analysis on Earth as well as on different planetary bodies. And this is a very characteristic graph that you would see, also called the structure function. So on the y-axis, you see basically the RMS deviation in meters, and on the x-axis, you see the horizontal distance between the two measurement points. And this plot basically tells you that how your roughness varies with the scale. And if you take the slope of the log of this plot, you get something like something called Hurst exponent, which I will explain in a moment. Now, taking inspiration from such studies, I also did a similar analysis for the four different subregions that I mentioned. And so here is the summary of the analysis. Now, let's come one by one. So what is Hurst exponent? It's basically the slope of the log plot of the graph that I showed you, and it basically tells you how the vertical roughness varies with the spatial scale. And the values of Hurst exponents varies from 0 to 1. The higher, the better. It means your the surface is strongly spatially correlated. And you can see from the table that the surfaces that I have chosen, the values are nearly similar and also towards on the higher side, which is good. But if you look at the RMS deviation of those sites, they change rapidly. So 4 meter scale means I'm just looking at the minimum baseline of my array size, and 178 meter is the longest baseline that I have. So I probe the two scales and I look at the RMS deviation values, and it changes rapidly. So what it also signifies that when you want to kind of choose a potential site for your array, you have to be mindful of both the values. You want to have low RMS deviation, which basically gives you the absolute amplitude of the local undulation, and also the Hurst exponent, which should be towards on the higher side. And that's how I just rule out the surface 1, and surface 3 and 4 appears to be good for me. So what I do with this, I'll come in a moment. Now, so basically, you saw that if we have such a surface and if we want to deploy an array, we have to heavily rely on rovers, and that might not go as planned. The trajectory of the rover might vary. Also, because of the local undulation of the topography itself, the array might not be situated on a plane, so as you saw from the elevation maps as well. So in that case, there might be imperfect antenna position, and so your antennas are right now not sitting on the planned grid, and that might impact your science case. And what basically I am doing is I am developing an end-to-end simulation pipeline to understand if we have such an antenna position offset, what would be the impact, and if we can quantify some threshold from there. So this is basically the schematic of my diagram. So the diagram of my pipeline. So what we can do right at this moment is we can give the array layout as an input. You can have a regular array layout, or you can introduce perturbations. In my case, I introduce a perturbation along XY direction using Gaussian distribution, and I also introduced perturbation along the height using the topography data. And then you can basically simulate the visibilities on the moon. And you can also give the sky model and the 21 centimeter model as your input. And again, do the forward simulation, do imaging of the sky, and then estimate the power spectrum. So that's basically the summary of this pipeline that it does. And these are the fiducial values that I have assumed currently for my simulation. And also I focus on these two particular frequency band. I know this is very cryptic. People won't like this value. It's really high redshift, and it's impossible. It's on the regime of impossible, but still it's very interesting to look at what might happen if we want to look at such high redshift. So yeah. Now the power spectrum. So what you see here are the 2D foreground power spectrums. On the y-axis, you have the K parallel, which is basically the Fourier mode along the line of sight direction, and the K perpendicular on the x-axis are the Fourier modes perpendicular to the line of sight direction. And so the summary of this plot is basically here. So all the foregrounds or the galactic synchronous emission that I talked about, because of their smooth nature, in this K space, it all gets confined to this wedge. Let's come here. It gets confined to this wedge. So whatever is left behind here in the higher towards the higher K parallel is the EOR signal that we are interested in. So basically, what we always try to do is to keep this window clean as much as possible and keep the foregrounds confined to this wedge. That's basically mainly the idea always. So this is what I get out of the simulations for the two different bands. And you can see that mostly they are within this buffer limit. And these buffer limits are set by a spectral window that we apply along this K parallel axis, which is also actually important, but I will not go into the details. Now, if there are this imperfection like this antenna position error or beam errors or any sort of errors that we don't want, they sometimes introduce spectral structure. So the foregrounds, which was initially smooth, now gets some spectral structures induced in it, because of which it no longer stays here inside the wedge, but it gets leaked into the EOR window. Yeah, and that's again not what we want. And through my forward simulation pipeline, I just want to quantify how much of this foreground is getting leaked into the EOR window because of the antenna position errors that I am simulating at this moment. So now for the perturbation along XY direction, we do not have any Z deviation, but it's just randomly scattered along the XY plane. So here I have actually analyzed with two different windows. As I mentioned, window actually plays a role. The reason being, in 21 centimeter cosmology, we are very much interested in the foreground mitigation strategy. So either you can, like going back to this plot, so either you can simply cut off these modes and just focus on this, and that's one way to mitigate these errors. That's called foreground avoidance. Another way is to be able to perfectly model what's here, and you just keep everything and then fit the foregrounds and mitigate the leakage. So depending on the foreground mitigation strategies that you use, the window also depends on that. So if you're going for foreground avoidance, like if you want to cut off this mode, you want a very aggressive window that keeps all the power inside this wedge. But if you're going for foreground subtraction, you can still, you do not really need an aggressive window, because you can then model, you can fit the foreground and just reduce the dynamic range. So these are the reason why I said windows are important, depending on the mitigation strategies. So here I analyzed two different windows. This is an aggressive window called Chebyshev window, and this is a relatively forgiving window, Blackman Harris. And I try to look at the different band, how much power is leaked into the EOR window and what's happening inside the wedge. So again, going back, I'm focusing on these two areas. And I will just, how much time is left? Is there?
1 minute.
Okay, I think it's not interesting to go through the plots. I can quickly just go to my summary slide. So what I learned from analyzing these two different windows and the two different bands is that the aggressive window was agnostic to all the perturbation ranges that I have simulated, at least for now. And it's agnostic in both the bands. But in case of the band that's not, the window that's not aggressive enough, that kind of introduced leakage into the EOR window, and it tried to set a threshold of 15 centimeter along XY direction and as flat as possible in terms of Z direction. So that's basically it. And the main conclusion is the perturbation level that we see right now is clearly below the thermal noise level. So it's not really harming our science cases as of now with the perturbation ranges that I have explored. So we are good to go for now. But yeah, we would like to again evaluate the performance of the pipeline using after introducing the thermal noise and also the beam model, which is again another source of errors in our science case. So yeah, still a lot of work needs to be done to be finally able to conclude how much of science we can do. Yeah, that's all on my end.
Very nice talk. Are there any questions online? The audience?
Just a curiosity. So when you were saying those age values and all this smoothness in the lunar surface, what does it compare to, for example, in MW site in Earth?
On Earth, I'm not sure about the MWA site, but on Earth, what I have learned is the value varies from 0.7 to 0.8.
It's worse than or better than?
It's worse. Like if you compare point with reference to 0.9, of course, it's a bit worse. Yeah.
Thank you for your talk. What were the plots you didn't show us? You can try.
Yeah. So these are the plots for actually different perturbation cases and also for the different bands and also different windows. So I'm just looking at the impact of this antenna position offset and how much leakage that causes because of choosing different windows, first thing. And also what happens if I choose different bands, second thing, and different perturbation cases. So in summary, what I tried to look is what you can even see here. Let me just compare two plots. So if I'm at the low frequency band and I'm perturbing along XY direction, the leakage in the EOR window for this aggressive window is relatively low. It's like below 10. This is the y-axis is the RMS of the absolute difference. So this is actually low enough. And for the Blackman Harris, this starts to show a trend after 15 centimeter. So it kind of what it says is it's introducing leakage into the EOR window as we are increasing the perturbation. So this window is not kind of agnostic towards the perturbation yet. Now, if you go to the higher band, now you see in both the cases for both the windows, the perturbation levels, the leakage level is way below the thermal noise. And the reason is because in this particular window, the strength of the foreground is 100 times less than the previous window I showed. So that also has an impact, and that's where the roll-up window comes into the picture, depending on the strength of the foreground you are dealing with and also the mitigation strategy you want to use. So yeah, that's basically it. Yes.
Right, sorry, a little bit unrelated question, but you mentioned that you were looking at the RMS value of sort of the size of the array and of the shortest baseline.
Yeah.
But I have some vague memory of videos of like foil being unrolled on the moon and that basically being the station.
Yeah.
Have you also looked at the RMS sort of on the scale of an antenna? Because I can imagine it deforms a bit.
Yeah, so right now, by the way, thanks for the next question. So the antenna length is 3 meters at this moment. So roughly I'm looking at 4 meters. So I can still translate this value to the
Nice.
antenna scale. So yeah, I guess that's my answer. Yeah.
Can I ask to what extent, because you don't have an atmosphere, so I guess stuff coming in from space, you have more of that, right?
Yeah.
That hits the, well, that hits the surface. To what extent is that a problem for, well, basically your whole setup? Do you think it will get damaged, or is there, I don't have a good feeling for the number of impacts that you can expect within your operating time. That thing?
Yes, that's the
Okay.
thing, that's the thing, and that's a research question that we have as a team, because yes, of course, there is no ionosphere, so there is always a chance of this micrometeor impacts. And so it really depends on what material you're using to build make your antennas. And for example, we are thinking of this inflatable antennas with because we have to be mindful of our mass. So there is always this trade-off, like lightweight antennas. Also, you have to have this, rigid material. So that's still a research question, honestly. We do not have a perfect answer to this.
I heard
If I can expand on that, I don't know how relevant it is, but I read a paper that said that you can build the telescope in deep craters in the moon, sort of shade, particularly from the solar wind, so that you can avoid charged particles hitting the antenna. I don't know how relevant it is, but yeah.
Yeah, but there are two downsides of craters, because of course we also trying to explore our potential side, the crater being. So you get this reflection, the multi-part reflection if you're inside a crater. So that's one thing. And the other thing is to be able to find a crater that has, like sunlight available, because if you're on the shadow, then it's very hard to have the electronics survive the cold nights, because it's almost minus 180 degrees Celsius, the
Oh,
lunar
I see.
night. So the question of survivability of the electronics comes into the picture.
Okay.
So whatever direction you look at, there is always a trade-off that we have to think about.
But what is the reflection thing you mentioned? I've never heard of that before.
So if you're focusing on the low frequency radio waves, so you have this huge ultra long wavelengths, right? And so if you're sitting in the middle of a crater, these waves would get impinge on your instrument, get directed towards the crater wall, again come back to your instrument.
I
That's
see.
creates a mess.
Okay, I see.
any other questions? Questions from online that we haven't seen?
I actually have something that I was wondering about. When you showed the images of the craters and I think you were showing that the altitude, variations in the altitude.
Yeah.
I was wondering how those measurements were obtained, like by what telescope or by what instrument?
Yeah.
Because it's on the far side of the moon, so we can't observe it from Earth.
So there's this orbiter called the Lunar Reconnaissance Orbiter. And this has been flying around the moon since 2009, and it has been instrumental in providing us this lunar topography data, because that's the best instrument that we have right now. So yeah.
Thank you.
Right, then time's up, so let's thank Sonia again for a great talk.